So good day everyone. Today we were going to discuss the Module 2 standard atmosphere. So why is it necessary to set the standard altitude? So whenever we design aircraft, we are going to analyze its performance and factors should be considered. For example, the properties of air such as pressure and temperature. We know that in different parts of the globe, the temperature varies and other properties will follow. It also for us to have a uniform terms in analyzing aircraft performance. That's why standard atmosphere existed. Standard atmosphere is used to easily compare for us to have a common reference. So we have the different types of altitude. So first, we have geometric altitude, which is the actual altitude measured from the ground or sea level. Next is we have the absolute altitude, means that distance from center of the earth. Next is geopotential altitude, known as fictitious altitude because it is altitude with no change in terms of gravitational acceleration. Also, it can be called gravity adjusted altitude. So we have pressure altitude and density altitude. These two are related to operation of aircraft. So pressure altitude is a type of altitude associated with ambient pressure, while the density altitude is a type of altitude associated with the ambient density. So last is we have temperature altitude, which has the same concept of the pressure and density altitude, but it corresponds in ambient or actual temperature. So is it possible to that geopotential altitude is equal or same in terms of value with geometric altitude? If yes, then when and how? So geopotential altitude and geometric altitude are related, but they are not typically the same in terms of numerical value. The geopotential altitude is generally not the same as geometric altitude in terms of numerical value because the gravitational field of the Earth is not uniform and it varies with altitude. However, at the specific reference points or surfaces, the geopotential altitude can be equal to the geometric altitude. So at sea level, geometrically defined as zero altitude. Geopotential altitude and geometric altitude are approximately equal. So next is over flat regions. In regions where the Earth's surface is relatively flat and the gravitational field does not vary significantly, geopotential altitude can be very close to geometric altitude. In simplified calculations, in some simplified calculations or models, geopotential altitude and geometric altitude may be considered approximately equal for practical convenience, especially in specific applications where the difference is negligible for the intended purposes. So, describe the relationship of the properties of air whenever the altitudes change. So, the properties of air change as altitude increases due to variations in pressure, temperature, and density. So, pressure. As altitude increases, atmospheric pressure decreases. So, in temperature, the relationship between temperature and altitude can vary. Temperature generally decreases with increasing altitude. This lapse rate is often referred to as the environmental lapse rate. Density. Air density decreases with increasing altitude. Density is the mass of air per unit volume and inversely related to the pressure and directly related to temperature. So now we are going to derive the and interpret the hydrostatic equation. So first, we note that uh, all forces are up. All forces upward are positive, while all downward forces are negative. Then uh, we assume that our condition is in the state of equilibrium because we are analyzing a fluid or air at rest. So first, we know that force is equals to pressure times area. Then we have uh, the force at the bottom, which is in positive condition since it is going upward, while the top force is negative because of the condition that it is going downward. So next is we have the weight of the air. So weight of the air, we have a force is equals to mass and area. So mass is equals to density times volume. Therefore, we have force is equals to negative rho volume. Again, we have force is equals to negative rho volume times the gravity. Then it became negative rho multiplied by area times difference in height multiplied by the gravity. Then we came up to negative rho times gravity multiplied by difference in height. So we know that the summation of so we know that the condition is in equilibrium state. So it means that all of the three forces acting on the acting is equal to zero. So we have the summation of all the forces equals to zero. Using algebraic expression, we now came up to the hydrostatic equation. So why is that the hydrostatic equation important? So hydrostatic equation is important because it tells us the relationship of the pressure in terms of altitude. Pressure is inversely proportional to the altitude. The more the pressure gets high, the more the altitude gets low. So next. So now we are in the problem solving. So at 12 kilometers in the standard atmosphere, the pressure density and temperature is given as 1.9399 times 10 raised to 4 pascals, 3.1194 times 10 raised to negative 1 kilogram per cubic meter, and 216.66 Kelvin, respectively. Using these values, calculate the standard atmospheric values of pressure, density, and temperature at an altitude of 18 kilometers. First, first is that we should write down the givens. So we have pressure at 12 kilometers, which is 1.9399 times 10 raised to 4 pascals. Density at 12 kilometers is equals to 3.1194 times 10 raised to negative 1 kilogram per cubic meter. Temperature at 12 kilometers, which is 216.66 Kelvin. Then we are going to find the pressure at 18 kilometers, then density at 18 kilometers and temperature at 18 kilometers. So we know that the problem is in the isothermal region since it exceeds the 11 kilometers of the gradient region. So the condition in isothermal region is that the temperature is constant at 216.66 Kelvin or 390.22 degree Rankine. So since we are using Kelvin, so we will be going to use the 216.66 Kelvin. So we are not going to find the temperature since uh, it is constant. So first is that we are going to find the pressure at 18 kilometers. So we have uh, we have the pressure at 18 kilometers is equals to pressure at 12 kilometers, which is given the 1.9399 multiplied by 1.9399 times 10 raised to 4 pascals multiplied by E raised to 9.8066 divided by 287.08 times 216.66 Kelvin multiplied by 18,000 meters minus 12,000 meters, which is our height difference. So our pressure at 18 kilometers is equals to 7,532.5900 5,097 Pascal. So next we are going to find the density. So we are going to find the density at 18 kilometers. So same procedure because uh, same procedure. The density at 18 kilometers is equals to 3 point uh, eh, 3.1199 times 10 raised to negative 1 kilogram per cubic meter multiplied by E raised to negative 9.8066 divided by 287.08 multiplied by 216.66 Kelvin multiplied by 18,000 minus 12,000, which is the height difference. So we have an answer which is density at 18 kilometers is equals to 0.1211 kilogram per cubic meter. So next. So next, consider an airplane flying at some real altitude. The outside pressure and temperature are 2.65 times 10 raised to 4 pascals and 220 Kelvin, respectively. What are the pressure and density altitudes? So first, we are going to write down the givens. So we have the pressure which is 2.65 times 10 raised to 4 Pascal. Temperature is equals to 220 Kelvin. We are going to find the pressure and density altitude. So first is that we analyze the problem. So first is we are going to uh, manipulate the formula of uh, the temperature variation. So we're going to find the height. So now we have the parameters. So we are going to get the height, which is we have a formula of H is equals to temperature minus the original temperature over the lapse rate. So H is equals to 220 Kelvin minus 288.16 Kelvin divided by negative 6.5 times 10 raised to negative 3. So we have the height of 10,486.15,385, which is below 11 kilometers. So it means it is in the gradient region. So now we are going to find the pressure altitude. So we have a formula of pressure over the original pressure is equals to 1 plus AH over the original temperature raised to 5.26. So we're, we're gonna input the givens. So we have 2.65 times 10 raised to 4 pascals is equals to 1 101,325 pascals multiplied by 1 plus negatives 1 1 plus negative 6.5 times 10 raised to negative 3 multiplied by the height over 288.16 Kelvin raised to 5.26. So we have the pressure altitude of 9,977.7424 meters. So next is we're going to find the density altitude. So for the density altitude, we have a formula of density is equals to pressure over RT. So we're going to input the givens. So for our pressure, we have 2.65 times 10 raised to 4 over 287.08 multiplied by 220. So we have an answer of 0.41958522914 kilogram per cubic meter. But it is not yet the answer. So we're going to get the use the formula of the density variation in gradient region. So we have the density over the original density is equals to 1 plus AH divided by the temperature at sea level condition raised to 4.26. So density is equals to the density at sea level condition multiplied by 1 plus AH over temperature at sea level condition raised to 4.26. So we're gonna input it and we have an answer of density altitude is equals to 9,858.34 meters. So that's all. Thank you.